data. So I think we looked at this example when we did confidence intervals, but we're going to look at it again from a hypothesis testing perspective. So the situation was we wanted to investigate if people's behavior is different on Friday the 13th, and we are comparing that to Friday the 6th as a day that does not have any superstitious significance. Comparing 2 Fridays in the same month in case the day of the week affects people's behavior. And they decided to compare the average traffic flow on these days. So our null hypothesis is going to be that the average traffic flow on Friday the 6th is equal to the average traffic flow on Friday the 13th. Our alternative is going to be that they are not equal. We don't have any pre-existing conception about the difference in behaviors. We just are testing to see if they're different, not whether that difference goes any particular way. So they got the traffic flow on the same location in the same month of the same year, one on Friday the 6th and one on Friday the 13th. Are these two counts independent? No, they are not, because traffic flow may be affected by the location. So if it's in the same location, then no, they're not independent. If we took a random sample of intersections on Friday the 6th and a random sample of intersections on Friday the 13th, those would be independent. But if we're doing the same intersections, then no, they are not independent. So that means this is a matched pairs. I don't know why. It's matched pairs. I need to fix that PowerPoint. So we're going to look at the pair-wise differences. Matched pairs. So we do the difference of the traffic flow on the 6th minus the traffic flow on the 13th, and we make a list of all of those differences, and that gives us a single data set. Now, that is a one sample, which we can find the mean and the standard deviation of. And it doesn't matter which way you subtract, but you have to subtract in the same order. So here we did the 6th minus the 13th. If there was no difference between the traffic flow on the 6th and the 13th, what would you expect the average difference to be? Should be 0, right? If there's no difference, the difference is 0. So, what are the hypotheses that we're using for testing the average difference between traffic flow on the 6th and the 13th? All right. The mean of the differences, our null is that the mean of the differences is 0. Our alternative is that it's not 0. This would be for a 2-sample hypothesis test. This is the difference of the averages. We want the average of the differences. That's our matched pairs. This is P. We're looking at a mean, not a proportion. This is X bar. We don't want X bar. We should always use mu in our hypotheses. So this is just like the one sample hypothesis test for a single mean. Now it's the mean of the differences, but it's still a one sample. And we're still testing to see if it is different from 0. So we do all of this. We do the differences, we find all the differences, and we plug them into our calculators and get an X bar of 1836 and an S of 1176, and our N is equal to 10. We're going to assume that this can be considered a random sample of differences. Our n is less than 10, or less than 30, sorry. N is less than 30, and we don't know the population, so we would have to check for skew and outliers. It's maybe a little bit skewed, but it's not extremely skewed. This does not look big enough, does not far enough out to be an outlier. So it's reasonable. The population of differences could be normal. We're going to go with it. On a small sample mean, you use a t statistic. It's t with degrees of freedom equals n minus 1. And so your t is equal to your point estimate minus your null value over your standard error. Your point estimate is your x bar, which is the difference, the mean of the differences, which was 1836. Your standard error is s over the square root of n, which is 1,176 over the square root of 10, which is about 372. So then your t is x bar minus mu 0 over sx over the square root of n, which is 1836 minus 0. Our mu 0 is 0. Over 372 gives us a t of 4.94. Degrees of freedom is 9. And, all right, null value is 0 because our null hypothesis was that mu diff is equal to 0. So then we find the p-value as the tail area under the t-distribution, right? If this is our t with a mean of 0, we got a t-score of 4.94 and 9 degrees of freedom. Remember that we were doing a two-tailed test because our alternative was that mu diff does not equal 0. So we have to multiply our p-value by 2. We're also looking at this tail of negative 4.94 for our t. So you multiply your TCDF by 2, and this gets us 0.8 times 10 to the negative 4th, which is 0.0008 as our p-value. So our appropriate conclusion, we reject the null. Our p-value is less than our alpha level of 0.05. So because 0.0008 is less than 0.05, we reject the null. We have evidence that the mean of the differences is not 0, which is to say there's evidence that the traffic flow is not the same on Friday the 6th as Friday the 13th. When we calculated a 95% confidence interval for this data, we got an interval from 995 to 2,677. Does the conclusion from the hypothesis test agree with the findings of the confidence interval? And yes, the hypothesis test found a significant difference, and the confidence interval does not contain the null value of 0, right? 0 was our null value. No difference would mean the mean of the differences would be 0. Our hypothesis test, we rejected the null, right? We rejected the null, which was that mu diff is equal to 0. Meaning 0 is not a plausible value. And it's not in our confidence interval, which also means that 0 is not a plausible value. So, yes, they agree. Do you think the findings of the study suggest that people believe Friday the 13th is the day of bad luck? Well, we can't say that. It's an observational study. All we observed was a significant difference between the number of cars on the road on these 2 days. We have not tested for people's beliefs. An observational study cannot be used to infer causation. All we can tell is that there's a significant difference between cars on the road. We cannot tell why that is. Another example. 200 observations were randomly sampled from the high school and beyond survey. The same students took a reading and a writing test, and their scores are shown below. Are the reading and writing scores of each student independent? No, of course not. Right? Some students who are good at reading are probably also going to be good at writing, and vice versa. We had 200 students, which our N is greater than 30. But if we do a histogram, we can see that these are approximately normally distributed. We don't actually need to do that, but we can. That's what technology is for. So we could ask, are average reading scores the same as average writing scores? But we would need to have two independent samples. We would need to take one sample of students and get their reading score, and one sample of students and get their writing score. Or we could ask, do students do better in reading or writing? Right? And then we would be looking at the differences. Here they did reading minus writing. The observed difference between the two scores, average difference between the two scores is negative 0.545 points, and the standard deviation of the difference is 8.887 points. Do these data provide convincing evidence of a difference between the average scores on the two exams? Use alpha equals 0.05. So, full 4-step hypothesis test time. So the first thing that we do is we state the parameter, which is the average difference in reading and writing scores for all students. We state our parameter hypotheses. We want to go ahead and state our statistic. Our X bar is negative 0.545. Our null hypothesis is that the mean of the differences is equal to 0. Our alternative hypothesis is going to be that the mean of the differences does not equal 0. We don't have any indication of which direction the test goes, so this is going to be a two-tailed test. And we're going to use an alpha equals 0.05. We plan. This is a one sample t-test for the average of the differences. We check our conditions. It's a random sample. 200 is less than 10% of all students. And our N is 200, which is at least 30. So that meets all of our conditions. Now we can do the work. Our general formula is that the test statistic is equal to the statistic minus the null value over the standard error. For a difference of mean, or a mean of differences, it's going to be t is equal to our x bar of the differences minus our null value, which in this case is 0, over the standard error, which is s over the square root of n. So s of the differences over the square root of n. And then we can plug our numbers in. Our x bar for the differences was negative 0.545. And we divide that by 8.887 over the square root of 200. And you put all that into your calculator, and you're going to get a t of negative 0.867. If you sketch your distribution, right, we're saying if the average difference is zero, the average difference is zero, what are the chances that we get something of negative 0.545 or lower, but it's a two-tailed test, so also 0.545 or higher. So our p-value is going to be the probability that our t is less than negative 0.867, or t is at least greater than positive 0.867, which is, we multiply our TCDF by 2. We'll do negative 1e99, negative 0.867, degrees of freedom equals n minus 1, which is 199. So lower bound, upper bound, degrees of freedom. And we get a p-value of 0.387. So what is our conclusion? If the null is true, that mu diff equals 0, there is a 0.387 probability of getting a x bar diff of negative 0.545 or less, or positive 0.545 or greater, purely by chance. So that's our interpretation of the p-value. Because 0.387 is greater than our alpha of 0.05, we do not reject the null and do not have evidence of a difference, or do not have evidence that the average difference, let's say, we do not have evidence that the average difference in reading and writing scores is not 0. Okay, so fail to reject the null. Data do not provide convincing evidence of an average difference between the reading and writing scores of students. All right, the correct interpretation of the p-value is that the probability of obtaining a random sample of 200 students where the average difference between reading and writing scores is at least 0.545 in either direction is 0.387. If, in fact, the true average difference between the scores is 0. Probability of incorrectly rejecting the null hypothesis, if, in fact, the null hypothesis is true, that is alpha, which is your probability of making a type 1 error. We don't know these things. there's no probability that the averages on the reading and writing exams are equal or different. So I guess it's better to say these things they don't exist. Either the averages are the same or the averages are different. There's no probability of that happening. The averages are what they are. It's just up to us to figure it out. Suppose we were to construct a 95% confidence interval for the average difference between the reading and writing scores. Would you expect this interval to include 0? Yes, we did not reject the null, which means that 0 is a reasonable value and so should be in our confidence interval. And that's it. Tune in next week or in the next 5 minutes for the hypothesis test for the 2-sample difference of means, which is our last hypothesis testing section. Woot. Y'all are going to make fun of me for saying that, aren't you?